Well, good morning, everybody. Again, I'm Hasan Aktarakçi, hosting this seminar from our European office in Madrid, Spain. And today I will show you some, as you know, all these, but just go through a little bit how you can do simple, like a 4-electrode measurement. And then the manually, how you do these 4-electrode measurement. And also I will show you later on the important things to doing all these measurements automatically. We will see that later on, the differences using this 4-electrode manually or 4-electrode automatically. But let's go through our first slide here. I hope everybody can hear me. And just go to the next one. Okay, what I will show you a little bit is the basic theory about these 4-electrodes. It's the same thing in, even if you do the multi-electrode, in everything is the same based on the 4-electrode measurement. But what today will focus more on this is the soil resistivity testing techniques, like the mostly used standard. Those standard as like typically ASMT 57 or the 81 is a engineering standard, and as well as all these are used for soil sample testings, as well as this mainly most of the time we have seen these questions coming from the cognitive protection, for example, grounding, all these things I will touch a little bit in each of them. I'll show you how you can do that. And it looks like the sound has gone off. Maybe again. Okay. Somebody couldn't hear you. Now he's hearing back. So I think it's okay now. So on these, we will see this soil resistive testing techniques, and later on some influence grounded metallic infrastructures, preventing and correcting field errors is mainly related is to 4-electrode measurement as well for multi-electrode measurements. Then I will make some comparison using automated version compared to manual measurements. As you know, this let me pick up my laser point over here. Okay, everything is based on two current injections, A and B, what you can see here, okay, A and B, symptoms here. So you need to inject current between 2 points, positive and negative, and then that current line goes to from A to B, for example, like this. And then if you go deeper and you go deeper. So what you're trying to measure is between two other points, which is what we call it potential electrode, MN. So that the other lines you can see is circles around the, let's say between B and A. This typically is what we call it is the potential lines. So what you're measuring is these potential differences between point M and N, as typically is corresponding with the midpoint of those measurements. So this is typically like equal spaced Werner configuration, like A and B electrode outside, equal spaced, and Mn is inside. So this is like a strong signal you get mainly for when your current is outside and then Mn is inside. So that corresponding point of this measurement, this is called pseudo plot point. It's not exactly, but is more or less where that measurement corresponding. Don't think about like a single point. Okay, those measurement is just average measurement. So it comes reflect all these area. So when you get one single measurement, it's not like just you go one single sample measurement. No, it's all average of this medium in covering in the area. Okay, but corresponding of that average midpoint is just right here. So just consider that one. Okay. So after that, when you have this pseudo plot or apparent, what we call it apparent resistivity values, we need to convert this to true resistivity values to get of this, let's say, the resistivity value of this point. So apparent resistivity is different than real resistivity. So everything like that, the homogeneous. There is no heterogeneity at all. Everything homogeneous. And then all apparent resistivity directly corresponds to true resistivity. But the reality is not like that. The reality underground is not homogeneous. There is also, there's lots of heterogeneity, and also there is a lot of directional changes. So that means is whatever you measure, you don't get like an exact real resistivity value. So you need to convert that to apparent resistivity to resistivities. Okay, this is the basic theory on all electrical imaging, DC electrical imaging. Okay, so like what you need: two current location, two potential location. That's all you need for either you do this manually or you do it automatically. So the other thing is like the using your instrument technologies is like a number of channels, increase number of measurement, and also that like a multi-electrode automatic switching make everything fast in the field, and those are different things. But the basic theory behind all this is like a for what is this soil resistivity testing? There are many different application areas, like agricultural studies applications. You may see that there are some areas they do like a very fast soil analysis because of the salinity in the ground and then dryness and the nutrition. And all are like related in somehow the resistivity as well, because of that moisture content in the soil, and is one of the dominant factor is changing resistivity values. So like agriculture, they are using it for soil analysis in using resistivity for resistivity measurement to determine these moisture content as well as salinities, for example. So there is like environmental analysis, detecting hazardous material presenting in the ground, and there are many. You may face many different contamination purposes studies is related on this mainly, and then you need to detect all these where the contamination is. Then electrical imaging also the use often. Geotechnical investigation is most of you have been using this technique in geotechnical investigation, but there are some 4-point measurement or multi-electrode measurement like a CPT measurement also you can do with this resistivity imaging, and I will show you how you can do with our system to do for like a CPT involvings. Like what typically is CPT is a cone penetrated test. So you can do laboratory testing, determine the velocity index in the how that soil content is, the salinities in it, in mineralization in it. So you can get the soil sample, and there is a soil sample box for the 4-electrode measurement. You just put your soil samples, preferably in situ, but you can do it in the lab also. To just get that the resistivity of the soil samples. So electrical engineering also used many applications, and especially for grounding grid, because you need to protect your buildings and the instruments and the equipment, everything from special lightning. So or the over voltage drainage in areas in these grids. So you need to find this ground and grid locations, and then checking your also ground and grid conditions. Another is the corrosion engineering. So measuring the soil resistivity to also help you to analyze this corrosion analysis under the soil. We will touch all this a little bit, but let's just go on the next one. So what is the next one is the most all these techniques what I showed, soil resistivity testing, manually you can do, and mainly it's two-way actually. These are actually, there are also the other third way, but the main is the ASTM G57 standard. You may see in this standard in some of the the licitations and the contract, they are asking you to do this kind of the measurement. This typically is described as Foret-Wenner method. So that either you do this in the let's say in lab measurement or institute measurement. So either you do like a sample measurement, or you do like a typically Foret-Wenner is like a typical vertical sound. Okay. So these are the typically what I should say is the Wenner method. So I'm not going to, I can show you this, what the standard is. This standard is, you need to purchase it. If you don't have it, you can purchase this standard on internet. There are many pages then they can obtain it. So those typically is like again Foret-Wenner and then manual measurement. The second is the IEEE 81 is 2000, what we call typically follow potential, FOP, follow potential techniques. So it's typically when your grounding system installed, it can be tested during the Institute of Electrical and Electronic Engineering. This is what we call follow potential method. Okay, so you need to check this, perform this grounding conditions, how well the grounding grid is performing, or how your cathodic protection system needs to be designed. So in this case, is like what you're doing in using this true standard to check it. So this can be done manually. Then also in third way to do all these things is automatically, much more efficiently. You can do that in the same thing and very fast. So my goal is to show you that, or you need to show you also to your client that, okay, I can do these standards for a Wenner measurement or follow potential techniques and the corrosion analysis and all these things. I can do it, but I can do it automatically faster, and then more information I can obtain it for the client. So that we will say that also. So is the first thing is like you can see here, what we have is the AGI soil box. So when you try to determine these properties of the soil, then you just get the soil examples on this box and connect this. This is like a electrode, B electrode, and here MN electrode. Okay, so you just get soil sample. It's preferable you get it on the field, or you preserve the field conditions of the soil when you're doing in the lab. So you don't want to change a field condition like a temperature, moisturized. Those are the main factor is changing resistivities. So then you get this in the soil samples, and then you analyze your in the soils. So again, this resistivity is depending on the grain composition, moisture content, and the composition of soil temperature. So what you get at the end, and on this sample over here, is like a our system designed to measurement this in general in centimeters, because of the area is fixed, and then we make this calculation automatically, and then you just easily convert that all this measurement to ohm meters. So like then soil resistivity will be reflected because these are the same thing, what you measure, apparent resistivity or real resistivity, because everything is homogeneous. There is no heterogeneity at all in here. I mean, it's in the condition. All material is same. So then typically this apparent resistivity measurement can be reflected in the real resistivity measurement. So then the values, for example, here, you can decide, okay, if my resistivity value is more than 100 ohm meters, so it's slightly corrosive. It is like a between 50 to 100 ohm meter, moderately corrosive. And these are like typically in this standard is you may see on the institute soil testing actually. So these are the standard also. I'm not sure if you can see it, but you can get it from the www.satm.org, and then you can put it again as standards/G57 HTM. So it can be obtained from there. So that soil testing can be done with MinSting with our instrument or SuperSting. So there are steps explain our user manual to do that. If you have these instruments, you can use this soil box, AGI soil box, and then do this kind of the soil analysis measurement. Okay, how you perform this 4-electrode ASTM G57 measurement? So what I said, this is a typical vertical electrical sounding. So you just need to do vertical electrical sounding instead of doing Schellenberger, but we get familiarized most of the time doing it easily Schellenberger. Now you need to do it in Werner electrode. That's like what standard requires. So like you need a center point or where your measurement, okay, and this center point, and then where the MN equals space A, and then between A and M is another electrode spacing A. So 3 electrode spacing is AAA, similar, and then currents outside MN. So you get first measurement. So typically here you connect this the first point and this one. So I can show you also here what the electric layout is. Okay. Then second measurement, you need to move this A electrode now is in the 2A electrode spacing distances. So that means it's if you're going this kind of measurement manually, typically you need about 4 or 5 people to do that. But if it is short distances, short A distances, maybe A distances up to 5 meters, 10 meters, you can do lots of walking and forward, backward. Then you change the positioning of the ABMN, and then just measure. But to avoid that, sometimes you need to have one person every electrode location. So the operator will say, okay, go to next point. Then it will go next point over here, yellow. And then next one. And in this case, it will go opposite. So that means you measure over here, first one, 2A, 3A, like this, and then going all the way up to where you want to measure. So you go further A spacing, you go deeper. So depending on your depth of investigation, you decide where to cut over here, where the A spacing will be. So it's not directly related. It's not like A spacing you're getting is the depth of investigation. So most of the people confuse that in my electrode spacing is almost depth of investigation. Actually, it's like half of the A spacing is the 52% of A spacing, your general depth of investigation corresponding in the range. So if you're doing this kind of things, this is the typical layout you can do. So I put it over here is let's say the walkthrough is the link where the help desk link. You can find it over here, and that help desk link in our web page is actually, when you get this in just to see all these steps how you perform Werner electric sounding with MinSting. This is the same thing is also SuperSting. So in new SuperSting, you have adapter box to connect this A, B, Mn electrode. If you have an older version super thing, you have a right over here on the front panel of the instrument, A, B, Mn, the connectors. So then you need to connect from A electrode, B electrode, M electrode, N electrode from here, or from the adapter box here. But the main thing you have all over here in the front panel. So this is what you do for electrode Venner measurement. You're all familiar on this, but I just want to go through a little bit. So the other thing is the cathodic protections. So like this, cathodic protections is generally what you do is let me go here one thing. Okay. So you need to protect, for example, pipelines. So like you have a buildings, bridges, and all infrastructures. So they are, what they are is the metallic, like iron structures. So those structures will be corroding with time. So then you need to design some protection on these structures. So there are typically is two type of the cathodic protections. One is called passive cathodic protection. It's like they install anode on the side of the structure, and then they try to protect the corrosion of these. Another is like mostly what we're going to show in here is what we call it is the impressed current cathodic protection. So this needs like a kind of the grounding, like to connect your current voltage injection to the ground easily. So that means what you need, the ground will be like a kind of clay zones areas. So in these clay zone areas can be done through these vertical electric sounding. If you're doing just for electrode measurement like manually. So either you do, like typically it's like, okay, the Venner, but you can also perform as the Schlumberger over here. So there's no the things. One thing what you do is sometimes you do in along this line, okay, where you're the design for your measurement. And sometimes it requires also the cross line of this measurement. Just make sure any variation on the area. So just like you can, based on this resistivity values in very corresponding your resistivity results on this like sections, you can also give this indication of the soil resistivity, like a corrosive zone and then slightly corrosive or severe area. It can be designed in this case. So then that will be help that designing of this the impress cathodic protection. So then that, because you already show that most conductive zone on the area, and then the company who's installing this cathodic protection, they know where to install and then how to install. Okay? So that like typically it helps for the companies who's using this kind of the installations. The other thing is the electrical engineering is standard, what we call it 81-2012. So this is what we call a typical fall-off potential ground testing. Okay. So that's like we need to show these structures, like what you need to protect your the structure. You need to protect the machinery. You need to protect for whatever is to be protected. Then you need a ground and grid. So like any over voltage, like a grounding has to be done properly. Because if you choose a ground very resistive, and then what happened is, in that case, the grounding grid doesn't work. So that means you cannot discharge your over voltage. So that means you start damaging your system. Let's say if any lightning come your building, and then this doesn't go to a discharge directly into ground, and then it will damage it. So if that grounding grid is located wrong place, or grounding grid already installed but past many years, and or past some time, because you need to check also this time to time, is very important locations, because that area is resistivity of the ground is changing with it depending of the rain season, not rain season, and the compactness and many other influences in the area that will change resistivity. So if the ground become like a more resistive, and then that you may get trouble. So that typically is checking all this and using this mini sting or super sting, you can use it. And here you can see in Unity Connect is the interconnect through this A electrode and M electrode shortage, or you can connect together to where your grounding grid will be located. Okay. When this grounding grid is installed, then this has to be disconnected first if it is already installed. Okay, so you need to connect for grounding grid from the building, and then disconnect first, and then connect to your instrument. Okay, A and M electrode has to be shortened or connect both of them on the same grounding grid. And then later on, you need to connect the current and this, and then will be shorted, as I said, and then place this another current electrode just away from grounding grid. This is at least 5 times from the grounding system. And so it's like it typically, for example, is the let's say 1 meter grounding grid or 3 meter grounding grid. Like a 3 meter, you should go at least 50 meters away. So 1 meter grounding grid, maybe you should go at least 3 meters away that B electrode from N electrode over here. And then you start separating this electrode probing distance, okay? And then you get the resistance measurements on this. So that measurement of the resistance, and here you can see here in the super sting manager application menu. And what you need to do is just you need to enter these values and the manual mode, and then it will be just go through the resistance mode and menu 2, and then will then from get directly resistance values. So that resistance values will be plotted with graphite with distance between probing distance, and then you will get your ground resistance interval. Okay, that where should be your ground resistance. So if your ground resistance is like a much higher or much lower, and then that will be your where the limitation has to be checked. Okay. Okay, this is typically how you find your ground resistance underground and or installations. Another 4 electrode measurement, what I call is like cone penetration test. The geotechnical studies you want to do is testing on the ground for geotechnically how that ground compactness, for example, and resistivity related with also that, and moisturized and compactness and all. You get that from resistivity values. So then it's typically either you do this is like a 4 electrode A, B is in the inside of the ground, N is outside. Okay, so you put the B electrode in the ground, and then get measurement, and then put your B is deeper and get another measurement. But it's typically is we will recommend to use this to multi-electrode. If you have a multi-electrode, for example, 20 electrode, put your 20 electrode on the ground, and then put your B electrode and some depth interval in a borehole, for example. You just drill and put B electrode, and then is typically on the surface. What you're doing is like a pole dipole measurement. Okay, this is typically the same pole dipole measurement. Only thing is my pole electrode location inside of the ground, not outside. So then I put this B and get all these resistivity distribution, and then lower the B, get another resistivity distribution, get lower the B, get another one. So until which depth I really want to be interested. So then I directly inject current from B in the ground to the surface. And then this really gives very high resolution of this the variations, and not only the resolutions but also the strong signal directly related into the ground. So then you'll invert all these data together. So this, you don't have to do separate data set. If you're using SuperString, for example, you can typically then put 20 electrodes on the ground, or if you do manually, which I don't recommend manual, but it's typically 20 electrode or more, and then lower that B electrode measured at the same data file, okay, and then keep that same measurement for different B location and the same data file without changing data file name, and then just invert it or the measures to the, and you'll get this to the section about which directly related, and you're the compenetration test. So another one is what we call is the logger, which is also 4 electrode measurement. We do have the AGI logger cable that permits to do short normal, long normal, lateral log measurements. And also you can do single point resistance or self potential measurement. Here you can see this, let me describe the cable first. This cable has design and all these like electrode configurations. Typically each time you use 4 electrode. So this is like here B electrode in the surface, and then you have another voltage is far away, and then you get this in A and B together, for example, short normal, and then you change this M position over here, you get a long normal. So different configuration is already done in different command file. When you have this logger cable, we send also this command file and related all these measurement, and they just lower down your cable where depth interval you want to measure. But this measurement location will be in the borehole saturated. Okay, so the borehole either has a mud or water. So unsaturated zone you cannot measure, so only be saturated zone. So you can also use this 4 electrode measurement and self potential or single point resistance, and it will also tell you where the if you use, for example, single point resistance, or typically what we call also contact resistance test, and you just get where the water level is. So the result of this, and you do, for example, graphics like this, Excel graphics, is it shows the SP. In this case, for example, it shows the short normal or long normal. So this is also is typically the 4 electrode measurement. By the way, this cable is like we have a 300 meter long feed-in on this cable, and that means you can use it up to 300 meters the borehole, and it's marked every 1 meter. So you either you go from bottom to up, or from top of the borehole to bottom, the direction of measurements. So every meter you lower down the cable, or you just pull up the cable every meter and then get measurement for every point, every 1 meter intervals, or every interval you want to measure in the field. So now I will show you the common errors in 4 electrode measurement. So like one of the common error is, okay, there's one question just came in. He's asking about this borehole logging. Does require special borehole casing. Okay, the borehole as you cannot use the metallic borehole, metallic casing, sorry. So you can use PVC, but that PVC has to be slaughtered or it has a hole. That means is the saturated zone water can permit that current go through from the inside of the PVC to outside. So that means you can use PVC if the borehole is not safe. Then you need to put casing. So if you want to put casing, put slathered PVC, which I mean is the PVC has a hole. Okay, what is the common errors in electrode measurement? And I have seen many times is the most common error is the geometry error. So, but you never realize this geometry error in the field. Because sometimes if it is short, even if short distance, I have seen this error. I got clients is doing very shallow studies, like 20 meters depth, 25 meters depth. So that means they are maybe a maximum 50 meters, and then maximum AB electrode spacing. That means 50 meters. They can see, but they cannot control exact locations. So like operators sometimes say, okay, I see what they are, but you're not sure if it's here or here. So this is like a typical error, because sometimes you said, okay, go to next point. So even if your cable is marked or ground is marked, it's difficult to you mark the ground, but typically what you do is you mark a cable and then you come up that next point. If the one of this operator is mixed, yes, very often they do, and then instead of staying over here, just stay there, but you never know. And then you just push your button, you measure. So you get your measurement. That means is that doesn't show any error on your measurement. Even if we recommend to repeat that measurement, that means the default setting comes to measurement, and then get in a standard deviation of 2 measurement. If it is the error like less than 2%, it permits you go to next one. If it is more, and then you repeat that measurement. In this case, sometimes you don't get it like an error on the measurement. So you really get, okay, very good result. I mean, very good measurement. That means is if you're not following your measurement, like a whole log graph like this here, this is a log paper, I really recommend to do it. Just use a log paper on the field and then mark each of your measurement. So for example, here typically is like a Werner or Schellenberger. And when you measure the first point, just put your dot over here. Second point, third point, like that, one. When you repeat it, and then your repeated value should be also around this point. For example, here, and you repeat it, and I got one up here, one down here. Okay, maybe sometimes you also get this to negative. So that means is you have a polarity issues. In that case, you may flip the MN electrode location. And then you correct this also the negative reading. Cannot be negative operator resistivity. So then just flip up these MN locations and the instrument, actually, not the field, and instrument connections. And then you just correct that negative operator resistivity if it is that related to polarity problem. If it is noise, so it's not there's no way to correct it maybe. So that means there is something wrong. So either this is a geometric problem or something influence on one of the electrode on some metallic structure or something. So my recommendation on the log paper, plot every point, just make sure you get right on the field. So if you don't get it right on the field in the office, you cannot correct it. So that means if I see something odd on my measurement, double check your location, okay? And then make sure also check your contact resistance. And then make sure also repeat your measurement. So that will save your some typically error on the manual measurement, vertical to the sounding. If you don't do that, oftenly you get this error. And then when you get this error, and then you don't know this point, because maybe here you don't have this middle point. You have up and down. You don't know which one, so you need to estimate that. So sometimes if it is lots of them like the same way, how you can estimate? I have seen this. The data sometimes it's just going in and up down. There's lots of changes between one point and another point. Cannot be sharp changes from one point to another point. It has to be everything smooth for vertical electric sounding. So if you don't get smooth curve, you're getting something wrong. You're doing something wrong. So other thing is typically for grounding grids you're checking, especially for electrical utility companies. They have grounding grids in the high power voltage towers, and also, for example, in recent day, you may see lots of the wind power around the electrical productions, and those are the wind towers also has grounding. So you need to check that grounding. So sometimes before installation, okay, there is no electricity on the wires. There is no static wire on the cables and between two poles, for example, when the transmitting electricity. So installing, okay, you can do this kind of the measurement, but if you're checking the installation grounding grid or grounding conditions, there is a power transmission. There's already static wire, and then this static wire comes in the ground just the drainage to over voltages. So that means if you're putting your line of measurement just close underneath, you're getting some errors, and you're getting influence of the static voltage, uncontrollable static voltage. This is what we call worst scenario in the resistivity line when you do parallel cross the grounded buried metallic infrastructure. What recommendation is you need to get away from this line. So how far should I get away from this line? So typically is electrical imaging is depth of investigation related is your total electrospec, like an AB electrode for a manual for assumption budget. So if I'm having maximum AB is 100 meters, that means I'm investigating about 15 to 25 meters depth. So that means 15% my minimum interval, right? So that means then 15 meters depth or 15 meters side I should go. So that what I mean is 15% you should go side of this line or transmission line to avoid this influence. The best thing is just go across if you can do that. If you cannot do cross, and then just try to remember, just go at least 15% the total spread of your line. I mean, total spread, 15% away from there. Okay. If you have a 100 meter spread, then 50 meters away at least. So that will avoid also that kind of the influence of your measurement. So this is true for manual or automated measurement. Okay. So what up to now, I'll try to show you a couple different things you can apply for electrode measurement. But these are strongly can be done easily actually, and strongly suggested, but easily can be done in the multi-electrode measurement. So if you have a multi-electrode, then you do it. If you don't have it, you just move your 4-electrode like this. You get because at the end you try to get not 1D image, 2D image, and then wrap that 2D image through 3D image to really understand how underground lateral variation is, not only vertical, because when you do 1D images and then you assume everything lateral doesn't change, but that's not true. So that's why when you do any of these standards in just doing in vertical sounding, at the end you're trying to analyze is under the ground. So maybe this the geotechnical purposes and engineering purposes or soil corrosion purposes. The important thing is to locate those in the interest is mainly for where the clay is in most of the cases what we are trying to see it, or geotechnical purposes, maybe you're trying to look at the cavities. So whatever your target is, you can do this for it to manually move around. So you need to move this from one point to another, and then another, come back, is changing. So you need to collect lots of data points. So each these data points is for electrode measurement, okay? And the first like you're moving like this and then laterally, and then expanding between spacing, and then get another line. So that means you have to do lots of measurement. So when you have to do this, is much better, because if you don't have this option, having this multi-electrode system, there's the only one option. So that you have to do it. Yes, you can do that. There is no way you can not do it. Yes, you can do that. I have clients has done this kind of things manually to 2D measurement. And I got a client that did like almost 1,000-meter type of investigation with this way. I got a client that did some mining investigation manually for a electrode moving around about a couple hundred meters depth. But if you have a multi-electrode system, then you can. If you don't, you can start with this way. When you make more money, you can add multi-electrodes on your system and then try to do this automatically. So when you do that automatically, what you need is you have a here you can see is like a 2D layout, like a multiple electrodes, equal spaced. That's typically what most of the time they use 56 electrode in our clients. But we have system 28, 48, 56, 64, 84, 96, 112, or up to you can put infinitely, I should say, because in limitation maybe 65,000 like active electrode we can use, or 65,000. There's no limitation at all, but the limitation is the budget. Limitation is, I mean, the purpose of studies. So sometimes you don't need that much. Maybe just 56 electrode or 112 electrode will be sufficient most of the studies. Of course, when you do 3D layout, and maybe depending on the 3D layout, you may need more electrodes, more than 28, more than 56. And all related to how electrode spacing is, how deep you want to investigate. So this typically 2D or 3D automated measurement. So like what we have is here's what our system uses: flex type passive cable, waterproof stainless steel takeout. It can be submergible underwater. We have here like comes a stainless steel electrode with spring. Easily you just tie it up and has a good contact. That's very important to improve your contact resistance. Make sure that this rod is inserted the ground is like a very tough stuck inside. It's not moving, it's not shaking. The other thing is that electrode has a really good contact with this stainless steel electrode. That's another issue to make sure that. Some people, they are just using this alligator clip, put this electrode on the ground, just put electrode alligator clips on this. But what happened, if I put it on the ground here, and then using this spare of this extension wire with alligator clips, and then just connecting the ground from here, also from here. So that means I am doubling up my current injection of measurement. So this depends also the area, it gives some error sometimes. Sometimes this corrosion, and especially alligator clips, it makes also increase the contact resistance. So some people just directly connect this to here out with this alligator clips. But I have seen this sometimes it get loose also. But you can decide whatever is convenient for you. But our recommendation is use this very tightly closed spring that push your electrode and keep your contact resistance is safely all during your measurement. Because in the field, when you do automated measurement, you're not doing 5 minutes measurement. Maybe you're doing a half an hour, 1 hour, 2 hours measurement. And then it will make sure that contact resistance really good during those measurements. Okay. So then typically what you get is these 2D sections. Okay. So these 2D sections, and really what you're trying to get under the ground. If I do this 1D electrical sounding or like a 4-electrode measurement, Schlumberger sounding, you will not get this to any lateral variations. You will not get this the variations in the under the ground. So what you may get it, for example, everything when I do 1D electrical sounding, everything will be blue at the top, same depth interval. You cannot get this variation of depth interval. You will get same depth. Second line will be, and second layer on the 1D electric sounding, with a more resistive, little bit like a yellow and green. So that means you will get it. You really not see these variations on this. Maybe then, if this 1D electric sounding, I will get just 2 layers. Maybe here just 2 layers. Maybe here just 3 layers. So that means depending on where your electric sounding is, you will only get that information. Even if you get average, and then that average will change the details of this one. Maybe if I get it over here, I'll really not get this maybe here, because I'm averaging also this high resistive and a little bit moisture, then it will all become green, not blue. That means I don't get this highly moisturized zone over here. If I am looking for it, which is this case, for example, they are looking for highly moisturized tree roots in the area. And then that means you really get that. But if I do vertical design, I don't get it. So whatever is the purpose is, it's important to do 2D studies and maybe later on 3D studies to really get these variations. Maybe at this point I see some questions, and I'll answer them based on this picture over here. Okay, just I want to ask if there is if device can estimate water level in aquifer. Okay, that the water level in aquifer is if there is a borehole, and then you can use our borehole logging cable, and then that borehole logging cable will give you the water level in the aquifer. But if you're doing just surface measurement, you have to interpret that water level where it is. Okay, I will show you later on a couple more examples related to that one. Okay, let me go another question. Is there a relationship between the length of electrode to the spacing in a multi-electrode system? Okay, let me just, is there a relation between the length of electrode to the spacing? Yeah, of course. I mean, the length of electrode, you mean this the stainless steel stakes, right? So typically what we're using 45 centimeter stainless steel stakes. And then just consider about, if you're doing laboratory measure, you cannot use that one. Because if you're using maybe 1 inch or like a 3 centimeters or 5 centimeters electrode spacing in laboratory, okay, in that case, you cannot use that stainless steel electrode I mentioned, 45. No, you need to use very, very thin nail maybe in that case. Just consider about don't put more than 10% of your electrode spacing. So what I mean, if you have a 1 meter electrode spacing, and then try to put your electrode into ground about maybe 10 to 15 centimeters. So that means it will make that as a point source. If you're very close, multi-electrode spacing is like if you do like a 1 meter, 2 meters, 3 meters. So depending on how that, and then you can put maybe a little bit more and more. So if I am doing a 5 meter electrode spacing, like 112 or 20, it doesn't matter. Then my rod is just 45, and I can put all the way down, because it's Typically in 5 meter, I'm just getting that one as a point source. If you put it shorter spacing more, and then it will become a line source. But that you don't really see that much in the field, actually, in the influence on your data. But just consider that. Keep that in the mind. Is just consider 10% more nuts. Okay. Okay. Can you tell me please about the capacity of needed power source for BH for resistivity logging up to 50 to 100 meters? So like a power source is our instrument. For logging cable, what we have is a super sting. You will use it, and is more than enough. What you're doing, like I got clients using maybe more than 1,000 meters in the borehole measurements, or more than 1,000 meters depth of investigation. They are using super sting. See, in the borehole is much easier in that case because your current and voltage is in situ in the ground. So that spacing also not much, because what you're trying to, you keep the same spacing for get high resolution information. So that means that your let's say like a short normal, long normal, lateral log, all these are like a very, very close electrodes each other, like a 16-inch, 64-inch separation. So that means you don't really need very high power output from the super sting. So this is okay. But if your question related from the surface, and then that also all related to a little bit how much current you can inject. But that's depending on all your contact resistance, which we talked that in the last webinar, last month, I think, how somebody asked that question. So that means is the contact resistance is the one of the determinant factor how much current you can inject. That means in that case, that current will permit you how much you can really go into the ground. Part of that is the geological distribution under the ground also. If you have a very, let's say, if you're working in the salty water, very salty water environment, then depth of investigation will be less. But if you're a little bit less, I mean the more resistive environment, you will go that. So how you can do that? You can typically check this 15% to 20% your total cable length of what you're using on depth of investigation. Okay, I will go the next one over here. I got more questions later on. We'll talk time to time. So here's an example as like a 2D 56 electrode modeling. You can also do that too before going to field. You just simply you model your underground like this, and this is the model come from Erdemir. You can model it, and if you're looking for example, conductive zone lenses, you can just do it, and then you can see what will be respond on this. So you can see that this influences is here. You cannot see in the upper text, but inversion, yes, you can see. Here you cannot see it. So that typically will let you know detectability of the anomalies. So that means you can do this kind of modeling for survey planning before going to field. Okay, earlier I got also some other questions, and this is somebody also sent me that. It says, imagine that geophysicals under pressure, how to guarantee that field results are reliable for opening the holes without yet interpreting software. This is his practical example, okay? So that means if you look at for example, this is like this different example, not this is the one, but I just put it over here. So your question is, can I use apparent resistivity directly without using software, right? No. Well, answer is no. Why? Look at over here, and this is like a Schellenberg electric sounding. Every dot is in the field measurement for different ABN spacing. So you can see ABN spacing is over more than almost 3,000 meters. So that means it's like a 2,000, 2,500. So that means in AB over 2 is 2, like AB spacing about almost 5 kilometers. Okay, in this vertical taxonomy. By the way, this is done within one of my clients in Turkey in Supersting R1 and for geothermal investigation. Okay, if I look at it, this point over here, the first point is about maybe where we located is 10, 20, 30, 40, 50, 60, like 75 ohm meters. And then it goes to here. When I look at it, this if I am just the first readings or corresponding my first layer, and I should say it, okay, I'm about 70, 80 ohm meter, less than 100 ohm meters, well, will be my first layer. But you can see that here, first layer is about 33 ohm meters, okay, on this model. So that means in here in my first layer, 33 ohm meters. Okay, maybe it's okay, I will maybe asymptotically, because if you know the shape of the curve, how the behavior of the curve, and then you can say, asymptotically, I can do that. Okay, I can do this asymptotically over here. Maybe I will estimate more or less. But this is not apparent resistivity, so that's your estimation. So that means now you're going to the true resistivity solution. If I go a second layer, my estimation will be over here, which is about 150. But what I see on this, my true resistivity, almost 457. So much more than higher than my estimation. So that means if I'm just using apparent resistivity to interpret that my data, no way. You have to invert your data. Whatever is 1D, 2D, 3D, you have to invert. Apparent resistivity cannot be used for interpretation, except when you do that soil sample measurement, in situ measurement, very homogeneous, like a soil sample is in the lab and in the soil box. Yes, that's exactly the same thing. But in this environment, it's not homogeneous, and there's also directional variations. So that means you cannot use it. You have to invert it. Okay, there's one question also before the temperature question. I'll ask water prospecting, if it is possible to use your device to estimate what depth from the surface you can find water. Yes, of course. I'll show you the next one. This one is also showing that actually. So this is done super sting if you're looking for water, and then this water interval, what will be, for example, my water will be about 31 ohm meters interval and this layer. So I have to find this layer is over here. So that will give you my where the water is. But this is not a water, groundwater. The next example is groundwater. I'll show you. The temperature question is there any effect of temperature on the recorder values? Because sometimes client asking record temperature. Well, we don't have this borehole logger cable has a temperature sensor. We don't have it. So if you have you can add it, maybe temperature sensor easily and the logger cable, then can be done. Maybe in the future we may do that, but at this moment we don't have any temperature sensor. So in order to get temperature recording, you need to have a temperature sensor. Okay, can you please tell me about the capacity of needed power source for borehole resistivity logging up to the power source is I'm sorry. The power source is just again, and if you're using Supersting, Supersting operated one battery or two batteries. The one battery is sufficient most of the studies. So when you use Supersting one battery, that means it's like you're powering up to 200 watt power output. So if you're using the AGI power supply, that's the same related with the battery. Instead of using battery, you use AGI power supply, then you just connect the generator. So the power source will be the same. It doesn't change. So that whatever you do, borehole resistivity logging or any others, Just most of the time, the battery power supply will be sufficient. Okay, what another question is, using the arrangement of 4 electrodes, how to effectively perceive that we are facing clay or salty water if values tend to be choose. Okay, I just brought this to as an answer of your question. And I received the question earlier with email. That's why I just prepared it. Here you can see that is a. Let's go to the first. On the top, what you see is blue, which is the resistivity values between 1.9 to about 10 ohm meters. So this typically is a salty water resistivity values. When you have a salty water inclusion in the area, resistivity values will be about very low. So depending on the salty water content, and then can be maybe less than 10 or 10 ohm meters, sometimes less than 1 ohm meter, of course, if you're in salty water in that case. So that means is in the whatever I have seen on the top, and then these are all breakage, which is salty water. So this is like a what we call it contaminated aquifer on the top. So when they drill, they get salty water. So if the client drill over here, and then they get salty water, when they come up to very resistive, there's no more water, and then there is nothing. They quit drilling if they don't have any geophysical this study. If they do drilling over here, same thing. Salty water, dry zone. Salty water, dry zone. Except two areas, like this is the fracturized zone. Okay, this fracturized zone, when you drill here, you really get where the aquifer is. The main aquifer is here, located underneath of this, like highly resistive, which typically I think is this limestones over here. So this aquifer will give you the fresh water in that case. So that will be, you need to be doing, in order to find this kind of, you need to do doing these 2D studies. If I do like a 1D electric sounding, okay, imagine I do 1D electric sounding over here. So at the top, I'll see all very conductive zone, then resistive zone. So I just get maybe 2-layer curve, not like this. This is not corresponding this one. Just give it an example. So that means if I do 1D, I just get like that section of the sections of the resistivity values, nothing else. So that means if your vertical sounding located here, you get just 2 layers. And then top is the salty water, and then limestone, dry zone. So that means it is how important to do 2D multi-electrode measurement over here. So that really need to know where to drill, and then how deep you need to drill, also important. So this example really gives you that one. Okay, another question is, in an area where the occurrence of limestone caves is confirmed as a 4-electrode arrangement, it can help to detect caves and fresh water. I speak of resistivity values. Okay, so again, I'll show you this through the 2D inversion results. So the same thing when you do 1D, just consider that in 1D you're limited with that infinitively horizontal same resistivity layers. Okay, there is no variations. So when you're looking for this like kind of the cavities, fractures, that means we're all talking about lateral variations. So that's really looking for this kind of lateral variations. Here's like a there is a cavity, dry, there is no water inside. And then also here's a fracture. If there's no water, maybe another cavity in this fracture over here, or maybe not, we don't know. So maybe here, another one cavity, maybe, but it's filled water maybe. So that's all. I have seen that some cavities we fill with water, some cavities filled with this air, and then it's really distinguished because really air-filled cavity is very highly resistive, and then water-filled cavity is drastically drop down that resistivity for some intervals, like less than, depending on the dominant factor. Okay, here's the dominant factor is the important, because I'm getting very highly resistive, like a small cavity in water fill, and then if I am having like a million ohm meter, then maybe I will drop down this the less than 1,000 ohm meter with water volume. But if it is the water dominant in the area, and then it will lower down less than maybe 40 ohm meter. So that's like all relative size, and then dominant whatever is the in the area. So that really you can speak about these resistivity values. Again, has to be converted to true resistivities. Don't forget that one. So you cannot use that apparent resistivity from that to determine where the cavity is, where the other things is. So another question is, what is the logical sequence of reading the various electrode sections? So for example, if the first reading was 2,340 ohm meters, and what reading can be expected? Okay, this is the same but I tried to explain it earlier. Just plot your all measurement on the log vertical electrical sounding, okay? And then when you're doing this vertical electrical sounding, and then you can really see where will be my next point is. So I cannot expect my next point over here. So expectation should be here. But when you're doing this multi-electrode measurement, how you can control that? There's an easy tool for this. If you have a supersting, and then we have created supersting manager applications. So that supersting manager shows you real time on the field how your that pseudo section to the pseudo section and in the color graph. So that means you're really seeing on the 2D sections on the field while you're measuring. And also you can see the values on the screen or on the tablet. So you can follow up your values, all measured values, and also the color scale, which is the sections. That really makes that the data quality controlling in the field. So this data quality control, you can do it like a 1D this way, what I described, or 2D, what we created supersting manager application to the tablet, Android tablet, for supersting only. Okay, I got more questions just came here over here. I got many questions. Let me go through. Okay, one quick question. Could you please give indication on the depth of investigation in this type of survey? Okay, I don't know which type of survey you're talking about, but whatever survey type is, depth of investigation, please consider always, okay? If you're on the seaside, because we have a system, supersting can be used land or deep ocean bottom studies as well. That means if you have a 500 meters salty water, and then you put your cable under the water, you measure it. So if you're that environment, or if you have a very close to seaside, very salinity water, very hypersaline water in the area, then you consider your depth of investigation maximum electric span, which typically maximum what your spread is, okay? So that like consider 15% of that. So if I'm expanding my cable 100 meters, and I can investigate about 15%. Which electrode array? Recommended electrode array. What is our recommended electrode? Dipole. Because our system is very high sensitivities for receivers. I mean, the receiver has a sensible to capture very weak dipole measurement. Because dipole gives you very good lateral variation, vertical variations. You don't get that with Venner. Don't use Venner, except you're obligated. Like they say, okay, this is ASMT 57 requirement. You have to do Venner. Okay, then you have to do it. But if you're doing like a geotechnical studies, groundwater studies, anything you're doing it, and recommendation to do this, the dipole with multi-electrode measurements, faster and also better resolution. Okay, so if you do Schellenberger, same thing. If you do the gradient array, same thing. So like a depth of investigation will be more or less same, 15% salty water environment. But in the land studies, consider typically 20%. You may get sometimes 25%, but it's better to be conservative a little bit, like 20%, 19%, between 15 to 20%. Your depth of investigation should be related to your cable length. Okay, another question. For water prospection, if it is possible to use your device to estimate what depth from the surface we can find water. Yeah, of course you can use, and as you can see the examples, those examples come from, I didn't show many examples, but just a couple examples come from all our clients, and then can be done through most studies from surface. Then you can estimate where the water level is, especially for the last one, I think. Let me just go back over here. So like this example, for example, here, you can really see where to drill, how far you need to drill. Okay, this is the interpreted area, fracture zone, where the groundwater is located. So if any surface water is involved on the top over here, and then for drilling, pumping the water from here, for capillary pressure, right? It just go from down here. So approximately here, what they have 100 gallon per minute, then the from water well over here. So that means is when you get this image, then you need to make interpretation yourself. That's the most difficult task. So as long as if you get the right image, the task will be easier, because you have already maybe background geological information, and then you really get very nice 2D section, maybe 3D section, then interpretation will be much easier. But if you have a 1D section, interpretation will be complicated, because you can show it where to drill, you drill, you then get dry. Because I have one client who do lots of groundwater investigations, and then at the beginning he was always doing vertical taxonomy. So like their success is less than let's say 30%, 40% when they do vertical taxonomy. And later on they switch everything with mutator system, and then still they do the groundwater investigation. But their success after that for 2D investigations, believe me, is about more than 90%. Okay, soil resistivity question. Temperature from 4 ppm nanometer soil. How will I can? Okay, temperature will be, you cannot, I mean, we don't measure temperature, but temperature affect your resistivity values, yes. But when you, this is like the important when you're doing really we're not talking about surface temperature, we're talking about the inside of the ground. So when you're doing geothermal studies, yes, when you like do vertical taxonomy or do this electrical imaging is and where the hot water is, and then that hot water, what it does is they lower the resistivity values, so become a little bit more conductive in the area. So that's only influence you may also get it, but you don't really see that how temperature. Of course, if you're doing in the lab, yes, you can do that. You can see that the different material, different temperature measurement, and the lab measurement. Yes, that will be the influence you can be done. I mean, you can control check your these in the temperature relation with resistivity values. But remember, temperature influence that reduced your resistivity. So I have been using SuperSting R8 for groundwater prospecting. However, having encountered some scenario where the data is clearly indicating areas of fracture. However, during drilling, they will have poorly encountered bedrock. Okay, this is like what I said is an interpretation. So that means is the first, what I will suggest is to do dipole first. Okay, just make a dipole and just get a section in the field. If your data is good, reliable, and satisfactory, and then you can go pick up everything, go home. If you get some noise, some not satisfied the result, you can easily add like a strong gradient. And then you combine later on strong gradient, because strong gradient gives you very like a high, because current since outside, you get like a strong signal, like a Venner, like a Schellenberger. So in that case, you combine that with the dipole-dipole, you get a joint inversion, and you get that section. So whatever is the section you're getting, for instance, you're getting section like here, and then you're getting these sections here. Where's my pen? There's a pen over here. So that means then you need to interpret that yourself. So like this interpretation is not easy, I know. Maybe you give drilling over here, you don't get it. You give drilling here, yes, you get it. So sometimes matter of the interpretation, how expert you are on this, and expertise is sometimes is not easy. So there's no way I can show you how to interpret that. But in that case is it's like a practice with time, and then you may need to do it yourself. Another question is, while using multi-rate automatic measurement, there has been this challenge of noise, even when the control measure have been. What do you think would be resulting? You're maybe doing just dipole first, okay? If you see that noisy data again, I will recommend to do maybe strong gradient easily. Just maybe dipole takes, depending on number of electrodes, maybe half an hour, 1 hour, and then maybe spending 10 more minutes getting gradient, strong gradient measurement, and then combination will give you a better result. So the data quality check has to be done in the field. So that's why like we created this recently developed modified superstring with applications, superstring manager applications. So the Android application helps you to control data quality in situ. So that means you make sure your data quality is in the good in that case. Is the dipole applicable to all geological formations, including complex geology, groundwater exploration? Yes. We always strongly recommend to use dipole and first everywhere. And deep ocean bottom studies for towing survey on the floating cable, and while going 2, 3, 4 kilometers per hour on the water surface, on the mountain doing mining investigations, on the desert area doing for geotechnical or groundwater investigations. Wherever you do, first recommendation, go to dipole for multi-electrode system. So if you have a single channel instrument, yes, dipole also recommended, but it will take longer time. So you better off timing, and you can do that. So the Asiki asking again, it is possible to upgrade older machine to use Android. Well, if you have older superstring, we don't have option to upgrade, but we have option to the offer for switching. So just send me that whatever you like, and I can offer you for trade in your old instrument, and then we can give you a new one. So we can just switch your old instrument with new one with some good discount. Okay, I think I already answered all the questions. If I already missed any question, please just send me your question with email. I will try to answer with that. So if there is nothing else, and thank you all for joining me today, our electrode measurement, but we start for electrode. As you can see, we end up with 2D, and I didn't show 3D result, but we end up all 2D, 3D automated measurements. So that's like what we need to do. So that means is the manual measurement is become very short. So we have to do it in 2D, 3D to really understand how underground is, how the variation is, not only vertically, but also laterally. So that will really help us to where to drill, where to find the target, what is the final result. So it will be easy to interpret that in that case. Okay, thanks again. And we will follow up later on with webinar, and when it is ready, maybe in a couple of days, we will send you also the recording. Thanks, and have a good day, everybody. Bye-bye.